In this video, we're going to find derivatives using the chain rule. For those who might not know, the chain rule helps us find derivatives of composition of functions. So if both f and g are differentiable and f is the composition defined as f of x is equal to f of g of x, then the composition is differentiable by doing f prime of g of x times g prime of x, or in Leibniz notation like that. So what that means is chain rule problems have layers, and we have to take the derivative of the different layers. So here's the first problem that we're going to look at. First thing I want to do is identify what my different layers are. So we see how I have an inside layer of x squared plus 1 and my outside layer of the square root function. So that's going to help us determine the derivative. First thing I'm going to do is rewrite the square root as a 1/2 exponent. So again, in the parenthesis notation, you can really see the different layers. I'm going to bring down that power with the power rule, 1/2 x squared plus 1 to the negative 1/2. Now I need to take the derivative of that inside yellow layer, and that's going to be times 2x. Not a lot of simplifying, just the 1/2 and the 2 cancel to get x squared plus 1 to negative 1/2. This is what the derivative, this is f prime of x. You could, as an alternate, rewrite it as f prime of x is equal to x over x squared plus 1 to the 1/2. Okay. Let's take a look at another one. Again, we're going to identify the same thing. My inside layer, I'm going for green this time, is negative x to the 4th minus 3. And my outside layer is all of that to the negative 2. So I'm going to do dy dx. That's the same as y prime. Negative 2. I'm doing the derivative of the outside blue layer in this problem. Negative 2 minus 1 is negative 3. Times the derivative of the inside layer, negative 4x cubed. And then just do a little simplifying. Negative 2 times negative 4 is positive 8x cubed. Negative x to the 4th minus 3, all to the negative 3rd. That's what our dy dx is equal to. Okay. Chain rule works from the outside in, just like Tootsie Roll Pops. You unwrap the Tootsie Roll, then you eat the candy, and then you have the Tootsie Roll in the center. So my inside layer is right here. That's going to be blue this time. My next layer is just to the 5th with this minus 1. And then my outside layer is there. So this problem has 3 layers happening because it's a composition 3 times. So my dy dx, I'm going to have 4 x plus 5 to the 5th minus 1 times the inside of the derivative of the next layer is going to be my yellow layer. 5x plus 5 to the 4th. Derivative of negative 1 will be 0. I don't need anything with that. Now I'm going to do the derivative of this inside layer. Derivative of x plus 5, derivative of that is just 1. So it really didn't change anything, but still good habit, because if it had been 2x plus 5, then I would have had a 2 on the outside. 20x plus 5 to the 4th. Since this is multiplication, I could have these in a different order as well. Okay. Oops, this one should have had to the 3rd. I missed the 3. That's my dy dx. So what we did there, we actually did the chain rule twice because we had 3 layers instead of 2. And it kind of, in that same nested notation, f prime of g of h of x times g prime of h of x times an h prime of x. And we're just unraveling this one layer at a time. We could actually incorporate these with the product rule as well. So the product rule says if this is my u and this is my v, uv prime is u prime v plus v prime u. Okay? So when I want to find the derivative here, so this is y equals dy dx is equal to derivative of the first one, 3x squared, times 2x plus 6 to the 5th, keep the second one the same, plus the derivative of the second one. Here's where that chain rule is coming into effect. 5 times 2x plus 6 to the fourth times another 2 times x cubed. Now, things I do not want to do. Multiply all this out to be able to simplify it. I hope you agree with that. 10x. But one of the things I could notice is that we have things in common. See, I have 2x plus 6 and a 2x plus 6. They have different powers on them, but we can still factor it out. Similar, I have x squared and x cubed. I can still factor out pieces on that as well. So I'm going to factor out a GCF of x squared 2x plus 6 to the fourth. Now what that will leave me with is 3. I still have 1 2x plus 6 because this had been to the fifth. So I had pulled 4 of them out, and I'm left with 1 on the inside, plus 10x. Okay? So now I can simplify on the inside here and have 6x plus 18 plus 10x, combine and say 16x plus 18. Way better than trying to multiply all of that out and then have to refactor it at the end. Here's another chain rule. We're going to do dy dx. I'm going to bring down the 6. 1 plus cosine squared x to the fifth. Now I'm going to do the derivative of the inside. The inside has this cosine squared x. It's going to be 2 cosine x times the derivative of cosine is negative sine x. Negative 12 sine x cosine x 1 plus cosine squared x to the fifth. Last problem for today, and this is a quotient rule problem. So just like we could use the chain rule within the product rule, we can use the chain rule within the quotient rule. So we're going to have g prime of x, okay, derivative of the high, so that's 3 cosine 3x times the denominator 2x plus 5 to the fourth minus the derivative of the bottom, low, 4 2x plus 5 to the third times 2, chain rule kicker, times numerator sine 3x, all over 2x plus 5 to the fourth squared. All right, now we're cooking. 3 cosine 3x, 2x plus 5 to the fourth, minus, on this side I have 8, 2x plus 5 to the third, sine 3x, all over 2x plus 5 to the eighth. You notice we have 2x plus 5 to the fourth, 2x plus 5 to the third, 2x plus 5 to the eighth. They're in common in all the pieces. So I can actually reduce them out. So I'm going to have 3 cosine 3x, and I'm reducing, the smallest power is 2x plus 5 to the third. So this one will have to the first left. This one won't have any left. And then the denominator will be to the fifth. 2x plus 5 to the fifth. Final answer. And that concludes our video on chain rule derivatives.